Modern processors contain a number of registers which are grouped together and they form a register file. You can see the block diagram of a register file shown here. So basically it's a stack of the registers, let's say, and in order to be able to have access to any of the registers, we need to have some address similar to what we had for the memory or RAM. Okay, that's something that we have seen already. So for the register file, we need to have a couple of inputs. We have the D data, which is the input data, and we assume that our registers, each one of the registers that we have, has a number of the bits. So if I show you one register here, which has n bits, all the registers that we have n bits, therefore the data input and output lines will have n bits, and that's what we have here. We have one data input line and we have two data output lines as A data and B data, and three of them, all of them have n bits for the bus, yeah, for the data line. Over here for our register file example, we assume that we have 2 to the power of k elements or registers, and each register has n bits of data. So our register file is 2 to the power of k by n register file. In order to access those, we need to have the address lines for our register including k number of bits, because with k number of bits we can address up to 2 to the power of k number of elements, and that's what we have here. Regarding the address lines, we have two address lines as A address and B address, and these address lines are used in order to determine which registers data will be available at the output of the register file. And we also have the D address, which also includes k number of bits, and it's the data address in it. Okay, D address is the data address, and it determines into which register we are going to write the input data. So this input data over here will be written into the register which is determined by this D address. And in order to tell the register file that we want to write the new data into a given register, we need to make this write or WR signal equal to 1. If we make it 1, it means that the data will be written. If it's equal to 0, it means that the content of the registers inside the register file is not going to change. For this configuration, we can read two registers at the same time because we have two outputs in it, two data outputs, as you can see here, A data and B data. We can provide a proper address for B address and A address, and therefore we will have access to the content of two registers at the same time. However, we can write to a single register at a time because we have a single data address here and a single line of data over here. So with write equal to 1, we can write whatever we have in the data line into the register which is specified by the D address. And you should also keep in mind that we are dealing with the registers. Yeah? So whatever we have here are the registers inside the register file. So there must be a clock signal. But for simplicity, we haven't shown it. Okay. Regarding the reading, we can read from the register file at any time. For reading, the data will be available at any time that we provide the desired address into BA or AA, and then the data will be available. But in order to write into a given register, we will write on the positive edge of the clock. Okay, so writing cannot be performed all the time, but reading could be done at any time instance. Over here we have an example of a 4 by n register file. 4 by n register file means that we have 4 registers and each register has n bits of data. So the width for the register is n. Here we have the registers R0, R1, R2, and R3. They are called as. And then in order to have access to these 4 registers, we need to use 2 address lines or address bits. Or our address line should include 2 bits, and that's what you see here. Let me just change the... Okay, so you can see over here, the address line, we have the data address 0, data address 1, and a multiplex, not a multiplexer, but a decoder is used here with enable to decode these address input in order to enable one of the registers at a time. Okay, so you can see that the outputs of the decoder, output lines of the decoder, are connected to the load input of the registers. All the registers are receiving the same data input, so they are all connected to this data input. You can see it over here, and the output data that we get from the registers, they are also connected to, because we want to have them available at the output, at the data output, they are connected to the input lines of 2 multiplexers. So here we have 4 to 1 line multiplexer, and here we have another 4 to 1 line multiplexer. The input lines to these multiplexers come from the data output of the registers, and in order to determine which register's data will appear at the data output, we use the addresses. So B address and A address here, and you can see that they have 2 bits, both of A address and B addresses, and that's similar to what we have for the D address. With the write signal, this is the control input. If it's equal to 1, then the decoder here will be enabled. Once it is enabled, depending on what we have on the D address, one of the registers will receive new data and it will be loaded with new data. Then on the other hand, depending on what we have on A address and B address inputs, the output data will receive value from one of the registers. As an example, if we have here 0, 0, then R0 will be selected and it will appear here. So over here we'll have R0, and if we have 1, 1 here for B address, 1, 1 means that the fourth in the input will be selected, and we will have R3 here. So we can choose which register to be available on the A data and B data. Here you can see the explanation for the register file that we just went through. We have the 2 to 4 line decoder, which selects one of the 4 registers for writing. If write is equal to 1, then the decoder will be enabled and one of the load signals will be active, and therefore the data will be written into the corresponding register. We have the n bit 4 to 1 line multiplexers. Okay, so we have 2 of them, as I already explained. One is here, one is here. We have the 4 to 1 line multiplexer. The number of bits on the input lines and the output lines is equal to n, which is the bits of the register, and with them we can have access to 2 registers at the same time. We need to be able, this is also important, we need to be able to read 2 registers at once, because for many operations, for many arithmetic operations, we need to have 2 operands as the source operands. Over here we have an example in determining the size of the decoder. So we want to determine what is the size of the decoder. The register file that we have is composed of 16-bit words. So the bits of each word is equal to 16. And we have 64 registers in total. We are going to use a decoder for the D address, similar to the design that we had in the previous slide, and multiplexers for the A and B output. Okay, for A and B output, we are going to use multiplexers, and the question is the size of the decoder. Since we have 64 registers, which is equal to 2 to the power of k registers, if we find out the value of k will determine the number of bits for our address line, and this number of bits for our address line will be here, and it will be indeed the number of the inputs to our decoder. Okay, so indeed k will be the number of the inputs to the decoder, apart from the enable, of course. So 64 is equal to 2 to the power of 6. Therefore, we will have k inputs to decoder. Our decoder will be in the form of 6 to 64 line. On the other hand, for the multiplexers, the number of inputs will be equal to 64. Similarly here. So our multiplexers will be 64 to 1 line multiplexers, and obviously the number of the bits for the B address and A address lines will be similar to what we have for the D address, which is 6. Okay, so we would need to have 6 select inputs for our multiplexers, and then we can say that option A is the correct answer for this question.